Hello, I'm Professor Afshar at Glendale Community College. This is Physics 101, Lecture 47. In this lecture, we'll discuss mechanical equilibrium. This topic is covered in Chapter 12 of our textbook by Surway and Jowett. We've used the word equilibrium many times throughout this semester. Roughly speaking, a system is said to be in equilibrium when the net force acting on it is zero. As it turns out, there are several different types of equilibrium, so in this lecture we want to refine our definition of equilibrium and make it more precise. We also want to discuss some of the important applications of the concept of equilibrium. To begin with, a system is said to be in translational equilibrium if the net external force on it is zero. This simple equation has a couple of important consequences. Firstly, if an object is in translational equilibrium, then the center of mass of that object cannot have any linear acceleration, or the linear acceleration must be zero. Furthermore, the linear momentum of the object must be conserved if the object is in translational equilibrium. These two facts are consequences of two important equations that we've seen before. Remember that Newton's second law of motion from Chapter 5 tells us that the net force is equal to mass times acceleration. For complicated systems with multiple components, the internal forces add up to zero, so the net force is simply the net external force. If the net external force is zero, you can see that the linear acceleration must be zero. We also know that momentum is mass times velocity, and when we take the derivative of that with mass being constant, we get mass times acceleration. So here we have another relationship that connects the net external force to a change in momentum, and if the object is in translational equilibrium, then this equation implies that its momentum must be conserved. It must be constant. Now, this is one specific type of equilibrium. Another type is rotational equilibrium. A system is said to be in rotational equilibrium if the net external torque is equal to zero. This equation has a couple of consequences as well. If an object is in rotational equilibrium, then the object cannot have any angular acceleration, or its angular acceleration is zero. Furthermore, its angular momentum is conserved. These two statements are consequences of these two equations, which we've encountered before. Recall that torque is the thing that brings about angular acceleration. This equation here is sometimes referred to as the angular version of Newton's second law of motion because it connects torque and angular acceleration. If the net external torque is equal to zero, then the acceleration, the angular acceleration, must be zero. Also, net external torque is equal to the rate of change in angular momentum. If the left side is zero, then the right side must be zero, and if the derivative of L with respect to t is zero, then L must be conserved. A third type of equilibrium is static equilibrium. For us, this is the most important kind of equilibrium. A system is said to be in static equilibrium if it is in translational equilibrium, and it is in rotational equilibrium, and it is at rest. So static equilibrium is essentially everything that we discussed on the previous slide, and furthermore, the object must be at rest. In other words, the velocity of the system must be zero, both its linear velocity and angular velocity. These conditions have some consequences, obviously. If an object is in static equilibrium, then we know that the net external force must be zero and the net external torque must be zero. That's by virtue of being in both translational and rotational equilibrium. Furthermore, the linear momentum is zero and it is conserved. The linear momentum is zero because the velocity is zero. Remember, linear momentum is mass times velocity. So the momentum is zero, and it will stay at zero by virtue of being in translational equilibrium. Also, the angular momentum is zero. Remember, angular momentum is moment of inertia times angular velocity. Since the angular velocity is zero, the angular momentum is zero, and it is conserved, meaning that it will stay as zero. Now you might be thinking this is a rather boring situation. Why would we ever be interested in static equilibrium? It kind of seems like for a system in static equilibrium, nothing much ever happens. And that's true. However, we often want situations where the system is in static equilibrium. For example, if you're designing a bridge or a house, you want those systems to be in static equilibrium. If you're designing a bridge, you don't want the bridge to move, you don't want it to have any linear velocity or angular velocity, and you would like it to stay that way. So this condition of static equilibrium is one that we often work very hard to achieve in various systems, and over the next few slides, you'll see some important examples of that. Let's do a simple practice problem involving equilibrium. We have three scenarios involving an airplane here. In each scenario, is the airplane in equilibrium, and if so, what type of equilibrium? In scenario A, the airplane is simply sitting at rest on the runway. So the airplane is not moving. We can say that its velocity is 0. And it is on the ground. There are forces acting on it, so we can say that weight is pulling the airplane down, like so. But of course, there is also a normal force pushing the airplane up, and these two forces balance each other out. They add up to 0. And so in this case, we can say that the airplane is in static equilibrium. It's in static equilibrium because its velocity is 0 and the net force acting on it is 0. There's also no net torque on the object, and the airplane is clearly not rotating in this case, so we can say that its angular velocity is also 0. In scenario B, the airplane is flying with constant velocity at cruising altitude. So the airplane does have some speed, but that speed is constant, and the direction of the velocity vector is also constant. There are forces acting on the airplane, to be sure. As usual, weight is going to be pulling the airplane down, but that force is balanced by the lift force. The lift force is essentially the force of the air pushing on the wings of the airplane. We haven't studied the lift force in this class, but the lift force is essentially the thing that keeps the airplane afloat. It turns out at cruising altitude, these two forces balance each other out. So once again, the net force acting on the airplane is going to be 0. However, the airplane is moving. Its speed is not 0. So the airplane is not in static equilibrium, but it is in translational equilibrium. These forces do not exert any torques on the airplane. The airplane is not turning or twisting or rolling. And so we can say that it is also in rotational equilibrium. In scenario C, the airplane is taking off from the runway. In this case, weight and the lift force no longer balance each other out. The velocity of the airplane is changing, so we can say the airplane is accelerating. Since it is accelerating, the net force on it cannot be 0. Therefore, in this case, the airplane is not in equilibrium. There are forces that are acting on the airplane. There are also torques that are acting on the airplane. As the nose of the airplane rises, you can see that the airplane is gently rotating relative to its center of mass. So in this final scenario, there is no equilibrium. Let's solve the practice problem involving static equilibrium specifically. A floodlight of mass 20 kilograms is supported in static equilibrium at the end of a horizontal beam of negligible mass that is hinged to a pole as shown. A cable helps support the light at angle 30 degrees. Calculate all forces acting on the beam. Now, this is obviously a situation where we would want to have static equilibrium. If you're designing a floodlight or a street lamp like the one shown here, you would want it to be in static equilibrium. Otherwise, something is going to fall apart and the floodlight is going to end up falling on somebody's head, a situation that we obviously want to avoid. In this particular problem, we're going to focus on the beam. Specifically, we will ensure that the forces are such that the horizontal beam here is in static equilibrium. We feel that if the horizontal beam is in static equilibrium, then the floodlight and the rest of the structure will also remain in equilibrium. We need to analyze the forces that are acting on the horizontal beam. The most obvious force is probably weight. Obviously, a heavy floodlight is attached to the right end of the beam, so we suspect that a force of weight must be acting on the right end of the beam. We can calculate the magnitude of this force because we have the mass of the floodlight. The right end of the beam is also attached to a rope, and that implies that there must be a force of tension acting on the right end of the beam. We know the direction of tension is oriented at 30 degrees relative to the beam, but at this point we don't know the magnitude of the tension force. We hope to find it. In addition to these two forces, there must also be at least one other force acting on the left end of this beam. After all, the beam is somehow connected to the vertical pole. We don't exactly know how the beam is connected to the pole. Perhaps they are welded together, maybe they're glued together, or maybe the beam is simply held against the pole by friction. We suspect that the contact between the beam and the pole must give us some kind of a force that is perpendicular to the pole. This might be something like a normal force. We also suspect that there must be a force in this direction parallel to the pole. This force might be something like friction that is holding the beam up. We don't really know much about the hinge and the exact connection between the beam and the pole, so we will simply at this point say that there is a hinge force and that the hinge force is pointing in this diagonal direction here. Notice that we're not really sure about the nature of the hinge force. It could be a combination of friction or the normal force. It could also be a combination of other forces. At this point, we're going to suspect that these forces add up together to give us this vector pointing to the right and also pointing upwards. We'll actually calculate the x and y components of this hinge force and develop a better understanding of it by the end of this problem. So at this point, these are the three forces that we suspect are acting on the beam, and we would want these three forces to give us static equilibrium, meaning that the three forces must add up to 0, and the torques due to the three forces must also add up to 0. We'll establish a coordinate system at the hinge point so that we can talk about torques. We'll begin with forces. Those are usually easier to write down. We want all the forces in the x direction to add up to 0. That's one of the conditions necessary for static equilibrium. In the x direction, of course, we have this mysterious hinge force, its x component, plus the x component of tension must add up to 0. Notice tension is pointing in the negative x direction, hence we have minus t cosine theta, and we want these two to add up to 0. We also want the forces in the y direction to be 0. This is another condition for static equilibrium. In the y direction, we have the y component of the mysterious hinge force. We have t sine theta, which is the y component of this vector here. And of course, we have minus mg. mg is the magnitude of the weight vector. We want all of that to add up to 0. Of course, to have static equilibrium, the torques must add up to 0. The torque due to the hinge force is 0. Remember how torque is calculated. The magnitude of torque is equal to the distance to the position of the force times the magnitude of the force times the sine of the angle between the position vector and the force vector. For the hinge force, you can see it is acting right at the origin, so the distance from the origin to where the hinge force is acting is 0. So the torque due to the hinge force is 0. The other two forces are a little more complicated. For tension, we can see that it is acting all the way at the other end of the rod, so it is acting at a distance L. Its magnitude is T, and the angle formed between the vector and the position vector is going to be 150 degrees. Remember, to measure the angle between two vectors, we put them tail to tail, and then we measure the smallest positive angle between them. This will end up being a positive torque inducing a counterclockwise rotation. Weight will also exert a torque. Its distance from the origin is L, its magnitude is mg, and once we put the position vector and the weight vector tail to tail and look at the smallest positive angle, we see that it is 90 degrees. We want the sum of all of these torques to be 0. However, note that weight will induce a clockwise rotation. In other words, the torque due to weight will be pointing into the page, so it is a negative torque. We now have three equations essentially for three unknowns. Our three unknowns are the x component of the hinge force, the y component of the hinge force, and of course the magnitude of tension is also unknown. At this point, we can do a little bit of algebra. We have a system of three equations, and we should be able to solve them for our three unknowns. We'll start with the easiest one. Equation 3 is actually the easiest one because we can immediately solve for tension. Notice that length of the beam cancels out. M is given. G, of course, is 9.8. So we can immediately solve for tension by solving equation 3. Equation 3 implies that tension is equal to 392 newtons. Weight, of course, was easy to solve from the very beginning. We didn't really need any of these equations to solve for weight. Now that we have tension, we can figure out Hx and Hy. We can take our value for tension, plug it into equation 1, and find the x component of the hinge force, and then we can put it in equation 2 to find the y component of the hinge force. When we do that, we find that the x component of the hinge force is approximately 339.5 newtons, and the y component of the hinge force is 0. So in fact, what must be happening is that the hinge force is not pointing in this diagonal direction as we suspected. It is actually simply pointing along the length of the horizontal beam. Its y component is 0, and its length along the beam is 339.5 newtons. Let's solve another problem involving static equilibrium. A ladder leans at angle 60 degrees against a smooth, frictionless wall in static equilibrium as shown. It has length 3 meters and mass 50 kilograms. Calculate all forces acting on the ladder. So once again, we have a situation where we want to have static equilibrium. If you're going to climb this ladder, for example, the last thing you want is for this ladder to accelerate, to rotate, or to move. Along with the ladder, you would move and you would fall. So we clearly want static equilibrium, and to achieve static equilibrium, the forces acting on the ladder must be 0 and the torques acting on it must be 0. These conditions actually allow us to figure out all the forces that must be acting on the ladder. So with very little information given in the body of the problem, with little more than the fact that the ladder is in static equilibrium, we will now proceed to figure out what are all the forces that must be acting on this ladder. Obviously, weight must be acting on this ladder. The mass of the ladder is given to us, so we know that weight must be pulling the ladder downwards. Gravity acts on the center of mass of the object, so we suspect that if the ladder is 3 meters long, then weight must be acting at 1.5 meters from either end of the ladder. Now the ladder is leaning against the wall, so it is making contact with the wall. Therefore, there must be a normal force acting on the ladder. This normal force is the force that basically supports the top of the ladder. Notice that the normal force, as always, is perpendicular to the contact surface. In this case, the contact surface is the wall. We are told that the wall is frictionless, that it is smooth, and so we know that there cannot be any friction on the top end of the ladder. There are also forces acting on the bottom end of the ladder. Obviously, the bottom end is in contact with the floor, and so there must be a another normal force acting on the ladder. This is the normal force of the floor acting on the ladder, and as usual, it is perpendicular to the contact surface. Now, as it stands, we suspect that there must be some friction between the ladder and the floor. We're not told that the floor is frictionless. And also, if you look at this picture here, you can see that there is simply no force to balance this horizontal force unless there is some friction. So we suspect that there must be a force of friction between the ladder and the floor, and we suspect that it must be pointing to the right. If it doesn't point to the right, then there will not be any forces that could possibly balance the normal force of the wall. This should make sense. After all, if the ladder were to slip and fall, the bottom point of the ladder would slip to the left, and therefore the force of static friction must be to the right. Of course, we'll do some calculations in a few minutes, and we will figure out the exact direction and magnitude of this force. Now, we want all of these forces to add up to 0, but on top of that, we want all the torques to add up to 0. Specifically, we have 4 forces, so we have 4 torques that might tend to rotate the object. We want all of those torques to add up to 0. To calculate torque, you should always have a coordinate system, some origin in mind. We usually like to put the origin on the pivot point or some hinged point or some point of the system that is stationary or fixed. In this case, you can put it anywhere, but probably the bottom end of the ladder is the most sensible place to put it. It will make your calculations quite easy, as you'll see in just a minute. Now, as I said, we have 4 forces, and therefore we need to calculate 4 torques. Recall that the magnitude of torque is given by this formula here. We'll start with weight. That's the easiest one usually. The distance of weight to the origin is half the length of the ladder, so L/2. The magnitude of the force is mg, and the sine of the angle between the vector from the origin to where the force acts and the weight vector is 150 degrees. Remember, the 2 vectors must be placed end to end, and the smallest angle between them is 150 degrees in this case. The torque due to weight can be figured. The direction of that torque can be calculated using the right-hand rule. Remember that the cross product of R and F gives you the torque. And if you use the right-hand rule, you'll see that the torque must point into the page or in the negative z direction. You can also notice that this weight by itself tends to rotate the ladder in the clockwise direction, and that kind of a torque is considered negative. So the z component of the torque is going to have a minus sign in front of it. Next, we'll talk about the normal force of the wall. This force is acting at a distance L from the origin. Its magnitude is unknown to us right now. We hope to solve for it, so we'll just call it n sub wall. And the angle between this vector here and the position vector, which points from the origin to where the force acts, is going to be 120 degrees. This is a positive torque because the right-hand rule tells us that the torque must be pointing out of the page. Also, this force tends to rotate the ladder in the counterclockwise direction, which once again tells us the torque is positive. The torque due to the normal force of the floor and friction is 0, so our final 2 torques are quite easy to figure out, simply because these 2 forces, and floor and friction, are both acting right at the origin where we placed the origin of our coordinate system. So the distance of those forces to the origin is 0, therefore the R is 0, therefore the torque is 0. So one virtue of putting the origin at the bottom end of the ladder is that it facilitates some of our calculations. We can immediately conclude that the torque due to friction and the torque to end floor must be 0. All right, now we are ready to basically add all of the forces and set them equal to each other. Also add all the torques and set them equal to each other. Continuing with our practice problem, we'll start with the sum of the forces in the x direction. If the ladder is to be in static equilibrium, then we want all the forces in the x direction to add up to 0. There are only two forces pointing in the x direction. There is friction pointing in the positive direction and end wall pointing in the negative direction. At this point, we don't know what F is and we don't know what end wall is, so this equation by itself is not very useful. However, we know that the sum of the forces in the y direction must also be 0. In the y direction, we have n of the floor, and we have w, which is pointing in the negative direction. We know the magnitude of w, it's simply mg, and this formula is quite useful because it can immediately be solved for n floor. To have static equilibrium, we also want the torques to add up to 0. In general, when you have 4 forces, you will have 4 torques. However, in this case, 2 of the torques ended up being 0, as we saw on the previous slide. So we really only need to worry about the torque due to weight, which is in the negative z direction, and the torque due to end wall, which is in the positive z direction. The sum of those torques must add up to 0. We now have a system of 3 equations for 3 unknowns: normal of wall, normal of floor, and the force of friction. We will start with weight. That's usually the easiest one. As it turns out, we don't really need any of these 3 equations to figure out weight. Weight is simply mg. That's an easy one. Next, we'll turn to equation 3. Notice that everything in equation 3 is known. The length of the ladder is actually unnecessary. You can cancel it out from both sides of the equation and immediately solve for end wall, and you'll find that the normal of the wall must be approximately 141 newtons. Next, we turn to equation 1. Now that we know what end wall is, we can immediately solve for friction, and we find that friction is approximately 141 newtons. Incidentally, notice that the value that we obtained for friction is a positive number, as we suspected. However, if in the course of your calculation you got a negative number here, then the negative is telling you that your original guess regarding the direction of friction must be wrong. It must be exactly the opposite of what you assumed. So the calculations in this particular method have this self-correcting mechanism where if the direction of friction was wrong, then you would simply get a negative sign to signal that mistake. And of course, equation 2 is an easy one to solve. You can immediately solve equation 2 and find that the normal force of the floor must be 490 newtons, exactly enough to cancel the weight of the ladder. And that's the end of this lecture. Thank you for your attention.